I was thinking one of these days I will just not start it properly and won't get recorded, but I guess that won't be a disaster. Right? It'll be a disaster for those who are relying on it. Is there more people coming, or is that it? Which is good, because you can have like almost one-on-one then. No, it's still not the same, right? Like watching it, you cannot really ask questions, or you cannot ask them interactively. You can still ask questions, but offline.
Although you can pause. Although I guess you could do that in real life by...
Yeah, I mean, we'll be shy, right?
Yeah.
Shouldn't really be. But still are. Yeah, it's trade-offs, really. I guess the best is to be here and then watch it.
This is probably the smallest class I've ever.
It is surprisingly small, yeah, for how basic material it is.
Yeah.
It's essentially like applied linear algebra, which I would expect more like 100 students or
I
something.
think a lot of people haven't heard of the class.
Ah,
So
yeah.
I'll tell people. I'm
Maybe
taking
then
it.
we need to do better marketing.
Yeah. And they'll be like, what is that?
Right. And it has some overlap with some math classes, which has the same material probably, but like from different angle, less applied, less matlaby, I think.
I'm not really related to that.
Okay, so let's get started then. I want to finish today the examples of linear systems. So what we were talking about last time was some cool examples of linear systems actually. And there was the Poisson equation or the Laplace equation. That was one very cool example. And what I was trying to explain is that this is using the discrete Laplace operator, which is essentially discrete finite difference approximation of second derivatives of a function. And there's like lots of calculus going on, but at the end of the day, when you want to compute it, approximate it using a computer, it just boils down to just a matrix problem, specifically a linear system solve problem. And not just any linear system solve problem. Maybe I will just recapitulate that quickly. Yeah, I think what I sort of finished, what was special about these examples we talked about the last time, like the Poisson, like the Laplace operator. The Laplace operator discretizes just the matrix, so another example of a matrix. So the Laplace equation or Poisson equation, the only difference between Laplace and Poisson equation is that Laplace means the right-hand side is 0, Poisson means that can be non-zero. The difference being that if I have like the stretchy rope with some extra weight hanging from my rope, that's a non-zero right-hand side, so I should be talking about Poisson equation. If it's like a homogeneous system and there are just zeros on the right-hand side, that's the example of like the heat diffusion, for example. That's all zeros. I just want it as smooth as possible. Then I have the right-hand side 0, and then we talk about Laplace equation. So this Laplace versus Poisson, it's not a big difference. That's the point I was trying to make. And the important thing to remember is that these very important matrices, the discrete Laplace operator, which appears both in Laplace and Poisson equation, that it leads to sparse matrices. And sparse meaning that they are like really sparse, meaning that almost all entries are 0. Do you remember for the 1D Laplacian how many non-zeros was there in the matrix? Asymptotically or even exactly, it's not so difficult to tell. So in every row of the matrix, in the 1D case, do you remember how many non-zeros were there? 3, exactly. Except for the boundaries, right? That the boundaries there were only 2. Correct. And in the 2D case, it goes a little bit up. So it's sort of intuitive, right? In the rope, every node was sort of influenced or talking to 2 other nodes, right? So there are three non-zeros. This node has the 2, and this one has the -1 or -1, or maybe the other way around. Doesn't really. Maybe it's this way. You know by now that multiplying an equation by plus or -1 doesn't make much of a difference. And in the 2D case, it was similar, right? So what was the number of non-zeros per row in the 2D case? Do you remember that? The 2D Poisson equation was the same idea, except that for a rope, I was like looking at some 2-dimensional structure. You can also think about it as like system of connected points in like 2 dimensions, like connected not just in the x-axis but also in the y-axis. So that was 5, right? In the 2D Laplacian case, the structure is not tridiagonal as before. It's not as simple, unfortunately, because the off diagonals they are a little bit further away, right? Like you can probably imagine it if I have like a whole image like this, and so I have one row here, another row here, yet another row here. So for example, this guy has its neighbors, he's looking at these, right? So it's not going to be just plus n minus 1 as in the 1D case, it's going to be also some minus n and plus n. Yeah, please close the door. Everybody's already here. Was planning on coming. So it's not going to be a tridiagonal system, but it's going to still be just every row will have at most 5 non-zero elements, which means asymptotically is just ON, right? If this is n by n matrix, all these matrices are square, which is nice. So the matrix has just linear as opposed to quadratic filling or complexity, right? If this is n by n matrix, I mean, so slightly confusing you here because here I was like drawing like the image, which translates to a matrix which would actually be like much huger n squared by n squared matrix, because all these things are degrees of freedom which I need to unroll in the vector. So I didn't mean to confuse you like this. I just wanted to make the point that the sparse matrices have only O of n. Do you know this notation? The capital O, I hope. Anybody doesn't know what is the capital O? Okay, good. So that means it's a linear number of non-zero elements. Okay, so let's move on to another very cool example of a linear problem leading to a solving system of linear equations. In this case, it won't be sparse. Did the images come out right? Yeah, it's pretty good, right? Surprisingly. I think the camera is pretty high res, that's why it's fairly good. Except for the focus. So radiosity. This time we will not get sparse matrices, interestingly, but we will still get linear systems, and there will be like some specialized ways to solve them. So what is radiosity? So radiosity is one of like prototypical or classical computer graphics problems. How to compute global illumination in a scene. So since we are in a scene, like this room would be a great example, and there are some light sources. Here would be some light. The windows would be other light sources. The projector would be the projector. There is another light source, right? Which are emitting light or radiosity. And we have some other surfaces here, right? Like the chairs and yourselves and the table and the walls, which are reflecting the light, right? Like typical examples, the projector. There is some light bulb which emits the light, and here it gets reflected and goes back to your eye, where you can actually see. The same thing for all the other lights, right? They really bounce around, and they fill, for example, that corner of the room back there. If there was no reflections, typically diffuse reflections, because not a lot of mirrory stuff going on here, it would have to be dark there, right? So the light goes there by light transport. The light bounces around the scene infinitely many times and super fast, right? It goes with the speed of light. Eventually reaches some sort of, I don't want to say equilibrium, but reaches some final lighting, final radiosity of the scene. That's what we see, and that's what we want to compute in radiosity in computer graphics. So there is, I mean, you could study this for a whole course, radiosity, but I just want to give you a high-level idea, and because it leads to another relatively simple linear system. But the first thing we need to do is essentially invoke like a finite element technique. Maybe I'll first comment on these images. So direct illumination is basically just like hard shadows. Like it would be just the first bounce of light. If there is some light coming through the windows here, and where it's not obstructed, it's in light, and where there is some obstacle, that's shadow. So you get like these hard shadow lines. With radiosity, the cool thing is that you get like a nice and smooth solution, because you consider multiple bounces. You consider the reflection of the light from all the surfaces. Like, so from the windows here, some light bounces off the ceiling and goes back to the floor, for example. And the way this is numerically done, the way this is computed, is that I take the scene and I discretize it in lots of small tiny elements, lots of small triangles. It could be also other patches, wouldn't have to be triangles, but triangles is the simplest thing to do. And then what we need to do is to formulate a system which will be telling us that some triangles are some of these, or finite elements, in this case just triangles. Some of them are emitting light, some of them are reflecting light, and what we want to find out is the final light on every, or radiosity, that's the proper term there, for every element. There are just some more examples. It really generates beautiful results. Radiosity was like back in the day, I'm not that old, I don't remember those days when like ray tracing was cool. There was the ray tracing, which was very good for these hard shadows, and radiosity was like the underdog method for getting nice and smooth lighting in the scene. So it belongs to rendering, to computer graphics. It's nice because you can compute nice images with it. But let's look at the formulas there. So it's another example of a problem that leads to a system of linear equations, and the linear equations look like this. So we need to talk a little bit about what these things are. So I already said we have some representation of a scene. The scene is triangulated, so there's like lots of small triangles covering all the surfaces on the scene. And we are interested in, or they are called patches here because they wouldn't have to be triangles, right? They could be like arbitrary polygons or even other things. There are some more subtleties in finite elements. Don't worry so much about it. The point is that we have like lots of degrees of freedom, finite number degrees of freedom, and we want to compute the radiosity on every single one of them. So on every single patch. So what we are computing is the BIs. That's the final radiance of each patch. That's what we will ultimately draw on the screen. Like high BI means it's gonna be bright, low BI is gonna be dark. 0 BI means there is no light, so it's totally dark, right? So the total amount of energy it emits. So how can we express the total amount of energy it emits? So the first thing is if it happens to be a light source, right? If it happens to be like a light bulb or something, then it's emitting something by itself. So that's the simple thing. That's the EI, the energy actively emitted by patch I. So that's only non-zero for light sources. EI. I don't need you to remember the details of this equation. You can always find it, right? I'm just want to get you an idea what all can be expressed as a linear system. So let's look at the sum. So what this sum says is that it's about reflecting the light. So Bj is summing over all patches, including itself actually, as it's written here. So it's going over all patches and aggregating the contribution of the light coming from all the other patches on myself, on the patch number I. So the other thing that's here is Fij, which is the form factor in radiosity. And what is it? It's the fraction of energy coming from J to I. So if I have like two patches, like one here and another somewhere over there, then I can compute essentially the fraction, the percentage, if you will, of light that goes from one patch to another. It's a purely geometric quantity. So I guess like if you have like one patch like this and another that would be like facing the other way around, and probably there is no light traveling to it, but if they are like facing, I'm not sure if I'm giving you the right analogy, but I think that's what it is. If they're like facing each other, then there will be like a high form factor. There is like a relatively complicated formula for this. It's like integral of some cosine terms. But at this point, you don't have to worry about that. This point is just a number. just a number that tells us how much light from patch Bj will get transported to patch Bi, because as the light bounces around. And R, the last thing here, is the reflectivity of the patch. So the fraction of the radiance that incoming versus outcoming radiance. Again, I could talk much longer about like modeling the material, and if this function gets much more complicated if you want to really consider what's happening in all materials. So this is just like a crude approximation, which essentially says that some patches are more reflective than others. If there's something like a mirror that will be like highly reflective, lots of the light would bounce off it, and with some like sort of diffuse, not very reflective surfaces, then the R would be very low. So again, it's just a number. So the high level picture, that's what's important here, is that the BI's are unknowns, and all the other coefficients here, there will be just some numbers. It would not be super easy to compute them, but once you compute them, all you have is just a linear system to solve. And the linear system, solving the linear system is equivalent to solving the light propagation in the scene. Interestingly, as you can probably imagine, the system is not particularly sparse, right? Because like if there is a light source, or if every patch can see every other patch, then these form factors, that's what the system really is formed from the form factors, that there will not be a lot of zeros between them. There will be a lot of non-zeros. So that's where there are some specialized solution techniques. Again, if it's computer graphics, you probably want the solution fast, right? You don't want to wait an hour if you like turn on additional light, or if you move a light source or something like that. There's actually a real-time radius of the solutions are becoming more and more popular in computer games. So this is something you want to solve in real time. So like you have a millisecond, something like that, to solve this thing. And you want, of course, as many patches as you can afford, because the more patches you have, the more accurate solution you will get. So this is something you will study. You can study in more detail if you go to take some graphics classes. But my point here is that solving systems of linear equations is a problem that occurs there very naturally. Any questions on that? I know I just was like sort of glossing over it, just to give you a teaser for radiosity and how it ties back to solving linear systems. All right, so let's get down to some more matrix business. There are some basic operations I still owe you. One of the basic ones is transposition. You probably might have heard of that. So let's discuss a little bit what is transposition. It's a very, very basic operation on the matrix. And it's very simple too. It essentially means swapping the role of rows and columns. Transposition can be applied to arbitrary matrix. It can be rectangular. Could be also square. Doesn't really matter. Can be applied to any matrix. Could be even complex matrix, or whatever matrix. In MATLAB, it's just this apostrophe symbol, so you might have already used it. And really all it is, so if I had a matrix in general with rows A1 to AN, then the transposed matrix is just A1. So I take the first row and I write it as a column, and the same thing I do for all the other rows. So previously, so now we have, so this is an example, right? If I have a matrix like this, 1, 2, 3 in the first row, that goes to the first column. Same thing for the second row. 4, 6, 7, the second row goes to the second column. So rows become columns. So notice that also row vectors become column vectors, right? I was previously not differentiating between row vectors and column vectors. I was previously like writing A1 could have meant both row vector and column vector before I introduced this transposition operation. But generally the convention is that unless specified otherwise, the vectors are column vectors by default. So you can quite frequently see this notation. A1T, AMT. that doesn't really mean anything but the fact that the A1 vector or all AI vectors were originally column vectors, and the transposition just flips them, let's watch this animation, like this. Just makes them row vectors. So this notation is fairly common, and from now on I will also use this notation. So if there is a vector, it means it's a column vector. I mean, this is slightly subtle, right? Linear algebra doesn't really care if it's a row or column vector, right? If we talk about linear spaces, vector spaces, they're just vectors. They are not a row or column, right? So this is just a convention about how do we understand it when we actually do things like matrix vector multiplication, right? Because matrix vector multiplication, you can use both column vectors and row vectors, right? If I have n by n matrix A, and assume now that it's square, n by n, then I can multiply it with a column vector from the right, if x is n by 1 vector, or I can multiply it from the left with a row vector, right? 1 by n, n by n. Right? And is it slightly tricky question? Is it the same thing? Ax as xda, a square. Slightly tricky question, huh? Are these two things equal? So this is multiplying matrix by a column vector from the right, and this is multiplying the same matrix with the same vector, but now written as a row, right? So the graphical picture is like this. This is my row, this is my matrix. Here, this is my matrix, and this is my column, right? The matrix vector multiplication is actually a special case of matrix multiplication, right? You can always look at vector as a 1 by n or n by 1 matrix, right? So do you think the result is going to be the same up to transposition or not? Yeah?
I think the first one should be an n by 1 matrix, and the second one should be a 1 by n matrix.
Yes, of course. So what I get from this will be, of course, a column vector, and what I get from this, and I'm out of space, but I'll just write it here, will be a row vector, right? The question is, if I transpose this, is it the same thing? It's not, right? But like, because let's try it. If I transpose this, what do? Oh, I need to explain this thing first. So I guess the question is, what happens to matrix multiplication if I transpose that thing? So let me explain this on this slide, and then we'll return back to that example. Those are things like so automatic that like just assume that you already know it. But actually haven't really covered. You probably know this anyway. So if I have a product of matrices A times B, it's a new matrix C. So if I transpose the product, I can also compute it as a product of transposed matrices, but very important thing, the order changes, right? So the transposition of product of A and B is equal to product of transpose B and transpose A, but the order matters very much. The order flips. That's super important to remember. I could also write it like, maybe it's clearer to write it like this. So AB transpose is B transpose A transpose. And let me explain you why that is the case. Again, I sort of prefer to like to explain you why it is so, rather than like construct like a formal mathematical proof. I mean, in this case, it's so simple that like the proof will very easily follow for what I'm going to draw. So let's look so if I have some example of matrix A, and they can be rectangular, they just need to be compatible so I can multiply them, right? So the number of columns of the first matrix must be equal to the number of rows of the second matrix. Let me do like a little, again, doesn't have to be, and that will be n by k matrix, and this is like my A, and this is my B. So I will look at the rows of A. So this will be my A1T and so on to AMT. And I will look at the columns of B. B1, so no transposition here because they already are column vectors, right? And BK. And this gives me the product of the two matrices, the C matrix, which is M by K matrix, right? And at a position I, at row I and column J, I have some element Cij. And what is the Cij equal to? You should know this by now. So what is the first element in that matrix? A1 and B1, right? Yeah. So the dot product I can conveniently write also using the transposition, right? So the C11, let's do the C11 first. It's just A1T B1, right? Because look at it, it's really just dot product. A1T means it's row, and B1 it's column, right? So matrix multiplication in this special case reduces to dot product, right? Because this is A1 was 1 by n, and B1 was n by 1, right? Otherwise it wouldn't really work, have to be the same size. And this is just a single number there, just a scalar, right? Because see, it goes like this, it goes like this. So matrix multiplication in this case is just a dot product. So this is also very, very common notation for dot product. I think I sort of prefer this notation for dot product than the little dot, because you need the transposition anyway. So this is just matrix multiplication. So you can just do a lot of things using matrix multiplication. So what do you think I have on position Cij? I think this will really be like a proper proof. So just arbitrary, the element in ith row, at row number I and column number J. So how the matrix multiplication works. Remember that? I take the rows from here, that's why I denoted the rows, and I dot product them with the columns from matrix B, right? And if I want element ij, then I take row number I from A, so I take AI dot product with column number J. Yeah?
Does it matter if it's A transpose times B or if it's A times B transpose, or is it?
So what are you suggesting? Oh, 8 times do like this. Let's do it for 1, right?
Yeah, would that work?
That's an excellent question, actually, and I will need another paper to explain that. That is a really good question. So A1 is like a column vector, right? And B1 is a column vector of the same size, right? So this is n by 1, and this is also n by 1, right? So A1T B1 is just a dot product, right? We were previously writing it like this. So this is a 1 by 1 matrix, right? Because A1T is 1 by n, and this is n by 1. So I have 1 by 1 matrix, one scalar. That's what dot product does, right? So very good question which you had is, what happens if I do this? Well, let's take a look what happens. So A1 is this, and B transposed looks like this, right? So that's very funny. What's going on here? So this is n by 1, and this is 1 by n. So I can still do the matrix product, right? Because 1 here and 1 here. It will be n by n matrix, exactly. So I will get this back. This is an n by n matrix, which is sometimes called the outer product of the two vectors. So again, it's the same thing, right? All I do is take, so if I want an element here, let's call it again Cij. So Cij is nothing but A1I times B1J, right? I take ith coordinate from A and jth coordinate from B, multiply them, and that's what this guy here is. So this product is sometimes called the outer product. I think we're probably going to talk about it sometime later, but cannot hurt. This matrix has some very interesting properties. It's a very special matrix because it was really born just out of two vectors. I think we will get to it at some point later. Now, you could also ask what would be if I took this, right? B1T A1. There are like four options, right? So B1T A1, that's good because this has to be also a scalar, right? And one trivial, but it's probably worth mentioning property of scalar. I can look at scalar as a 1-by-1 matrix, right? And if I transpose 1-by-1 matrix, I do nothing to it, right? There's really nothing to swap, or the rows already are the columns. So if I interchange the role of rows and columns, I just get the same thing, right? So I can as well transpose this entire thing. It's just the same because it's just a scalar, right? And if I transpose it, remember this rule, which I was in the middle of proving while I got this question. So from this rule, I can write that this is A1T and B1 transposed twice. But if it's transposed twice, then it's again the same, back at the same thing, right? If I flip it twice, then I'm back to the same thing, right? I first flip it to column, and then I flip it back to row. So if I do B1 transpose A1, it's exactly the same thing as A1 transpose B1. And it's a scalar. It's a 1-by-1 matrix. Now what would happen if I took B1 A1T? I think it's going to be a transpose of this matrix. Yeah, will be a transpose of that matrix. So here is your answer. But let me finish this proof, which I already used this property there. So if I'm taking a product of matrices A and B and they look like this, then the element of the product on row A and column J is a dot product of AI times Bj, right? And now I need to look what happens if I do the same thing with the transposed matrices Bt and AT. So let me try to do it like this. That will work. So what do I need to do is take Bt. So I will transpose, oops, wait, here. So I'll transpose B. So what are going to be the dimensions of transpose B? So this is my Bt. What is it? Well, K by N, of course. K by N. So it was N by K. If I transpose it, the row of columns and rows swap, right? And so if I'm looking at the rows of B, then they will be just B1 transpose. The columns of B became the rows of Bt, right? That's how we define the transposition. And this is Bk transpose. Now I do the same thing to A. So this is my A transposed. What's the dimension of A transpose? N by M, right? So the product, fortunately, is well defined, right? This N is the same as this N. That's good. And again, the rows of A became the columns of AT. So I have A1 here, no transpose now because it's a column, and AM here, M columns here, right? And the product is going to be some K by N matrix. This is my CT. That's what I'm trying to prove. So not right now I just know it's K by M, right? And what is going to be in, let's call it D. Dij. So what would be the Dij element? So first, let's do D11. That's slightly easier to. So D11 is what? Yep, B1T A1, of course, which is So I was just explaining the same as A1 TB1, right? Which is exactly what was C11, right? Oops, put it a little bit more. C11, right? And D, actually might be better to look at it as D JI. So let's say that the J indexes the rows here and the I indexes the columns here. So if I have DJI is gonna be BJ transpose AI, right? If I take the jth row in ith column, then I'm looking at jth row here, which is BJ transpose times AI, right? Which is exactly AI transpose BJ, right? And that's nothing but our Cij, right? So this matrix is nothing but this matrix transposed, right? That's another way how you can write a transpose. This essentially means that the role of rows and columns is swapped, right? I just swap the two indices and I get the D's. That's how it. You can also notice that this work. This is m by k and this is k by m. So this was to prove that the transposition of product is product of transpositions in the reversed order. That is very, very fundamental, very important property. Now we finally get to discuss properly matrix inverse. I already told you a little bit about matrix inverse, but I think I didn't tell you how to actually compute it and what properties does it have, except for some special matrices. So now we will explain how to compute matrix inverse in general, if it exists. So first of all, so remember this, transposition was defined for any matrix. Could be rectangular, could be complex, whatever. Inverse needs a square matrix. There are some notions of like pseudo-inversion for rectangular matrices. We'll talk about this later. But when I talk just about inversion, I mean of a square matrix. And the inverse matrix is a matrix such that when multiplied with the original matrix, it gives me identity. You remember what is identity, right? In a little bit, or maybe see if today or on Wednesday, we'll prove that if if this is true, then this is also equivalent to A inverse A. It doesn't matter if you invert it from the right or from the left. In both cases, you get the same thing, which is identity. We talked about matrix inverse a little bit before, but how do we actually compute matrix inverse? Actually, by now you should be able to tell me how to compute matrix inverse. Because, well, maybe I can do it here, right? So how would you compute inverse to matrix A? So what, again, it helps to think about it graphically. So this is our matrix A. Has to be square, right? So that's why it's nice to like draw it, because you see it's square immediately. And here is some unknown matrix that's going to be the inverse matrix. It has to have the same dimensions, has to be also squared. If this is n by n, also has to be n by n. And it has to give me n by n identity, right? So it means in the first column there is 1 and the rest is zeros. The second column there is 0, 1 and the rest is zeros, and so on, right? That's what the identity matrix is. So this is n by n identity, right? So how would I find the first column here? Let's call it x1. Now you should be able to tell me that. Because yeah?
Would it be first row of matrix A, and every element is the inverse numerical scalar inverse? Like if like A11 is 7, then A inverse 11 would be like 1 over 7?
That might work in some special cases, but not in general, I think. in general, you need to think about more in terms of solving linear systems. It's essentially a linear systems problem. You could try that, but I think not in all cases this would work. So if I forget about the remaining column, you remember that matrix multiplication is just a sequence of matrix vector multiplications, right? Doing ax1, if there was another one, ax2, and so on, right? That every column here can be computed as the corresponding column here times a, right? That's what we discussed when we were. I think that's how we even defined the matrix multiplication. So this computing x1, just the first column of the inverse, that's just asking for this, right? So we are asking what is the vector, column vector x1, such that when multiplied with a gives me this e1, the first standard basis vector, right? That's a linear system problem, right? I know a, I know this right-hand side, and if I know how to solve a linear system, then I can just solve for x1, right? And sometimes it will be as simple as you were saying, but sometimes the system might be a little more complicated depending on the structure of A. So guess what happens for x2? Probably very simple to guess, right? I'm just solving a slightly different linear system. Actually, the linear system has exactly the same system matrix, it only changes the right-hand side, right? So in other words, finding an inverse matrix can be accomplished by solving a set of linear systems of linear equations, where the only thing that changes is the right-hand side, and the right-hand side are the standard basis vectors, the e1, e2, and so up to en. Got it? I'm still impressed you are still taking notes. Not good for you. Actually, what I would probably do or suggest is to take the notes from the video if you really insist on that, because this all is recorded. And yeah. Well, no, there is the website for this thing, and there is a link to YouTube. Even if you like search my name on YouTube, you should just find it. Or ES205 on YouTube. I don't think there is many more ES205s somewhere there. So here is an example. Let's take a look at an example. So I have this matrix, 3 by 3, simple matrix, and I want to find its inverse. And as I said, finding its inverse is equivalent to solving these 3 linear system problems. And the only thing that changes there is the right-hand side, and the right-hand side are exactly the standard basis vectors. So I'm not going to do the solve. You could do it in MATLAB, for example. The MATLAB can compute the inverse very easily, right? You just do inf a and gives you the inverse. But you could also do this, and maybe you should try just for fun. It only takes like a minute. Is to just do the x1 equals a backslash this, right? And then you would do x2 equals a. I'm writing the backslash right, and x3 would be a backslash this, and then the inverse better be equal to x1, x2, x3. I hope I write it correctly in MATLAB. My MATLAB foo is not so strong as yours, probably, you know. So this is the solution I would get if I just did this. Just solve this linear system. This is my solution, and then the inverse matrix, I just stack them together. So the first vector x1 comes as the first column, the second column, and the third column, and this is my inverse matrix. Now, one thing that's very often discussed in like the context of solving linear systems, once you like learn about the inverse, then you like tend to just use it everywhere, because once you have the inverse, then solving linear system, if somebody gives you some new b and you have the inverse, then there's nothing easier than to multiply it with the inverse, right? And this is identity. So you have that x equals A inverse B. In other words, the inverse matrix is the solution operator. For arbitrary right-hand side, it lets you very quickly to compute the solution. Right? Do you see that? But if you just need to solve a linear system like this, like for example from radiosity, right? We have just, and I have just like one lighting, one b vector, one right-hand side, where the right-hand side corresponds to the emittance, to the radiosity due to the source itself. So I have just one. So it would be sort of inefficient to find the inverse matrix just to multiply with the b1s, right? It is typically more efficient to just solve the linear system once rather than finding the inverse. And from this you should have an intuition why, because finding the inverse is essentially equivalent to solving the system n times, right? For all of the standard basis vectors. So if you have a 3x3 matrix, you essentially need to solve it 3 times. But if you only care about one special right-hand side, then you don't really need to solve it 3 times. You only need to solve it once for the specific right-hand side. So the matrix inverse, as I was saying before, does not always exist, unfortunately. There are matrices that are not invertible, right? We were talking about some examples before, like if I do, for example, this, there's no way you could find a matrix that would give me this, that would give me back identity, right? Because here I have 2 zeros, so no matter what I write here, I have to get 0 here, so that's impossible. So when matrix does have an inverse, that's a very important question in linear algebra. So necessary and sufficient condition is that if I do Gaussian elimination with partial pivoting, then all the pivot elements must be non-zero. If they are non-zero, then the matrix inverse exists. And that also guarantees that I can find a solution of this system of linear equations. We have discussed that when we are talking about LU decomposition. So this is one way how you can test for a matrix if it is invertible. MATLAB would also do that for you. I'm not sure what the inf function does if the matrix is not invertible. I think it complains or something like that. Now here is another interesting thing. So when I was talking about transposition, we said that AB transposition is BT8T, right? The same or the analogous property is true for matrix inversion, assuming both of them are invertible, right? In transpositions, for granted, everything is transposable, but not everything is invertible. So if I have matrices A and B that are invertible, then I can say that the inverse of the product of A and B is the inverse of B times the inverse of A. So it's really, it has the same format as the transposition. Again, remember this has to flip. That it's first B and then A. Or more like first A and then B, really, because it's applied from the right, usually. And why this is true, it's sort of trivial to prove it. So if I have AB and I multiply it with B inverse and A inverse, then due to associativity, I can write the brackets like this, right? And because B inverse is identity, the identity disappears, and I'm left with A inverse, but that's also identity, right? So that means that C, so this proves that this thing indeed is inverse to C, because it gives me back identity. And this thing was B inverse A inverse. So B inverse A inverse is the inverse of AB. That's what this is showing. And there is one special class of matrices where this looks suspiciously similar to transposition, right? And actually, for certain special class of matrices, transposition is exactly the inverse. In other words, to compute the inverse, all I need to do is transpose. This is only true for orthonormal matrices. Just to remember what were orthonormal matrices, that's what we started with, I think, when we were talking about dot product. Like rotations were orthonormal matrices, right? We had another example of orthonormal matrices. The permutations used in LU decomposition. And what it means, orthonormal matrices, means that if I take the dot product between any two rows or any two columns, I get either 1 or 0, depending if it's the same columns or if two different columns. I think I will need to explain this a little bit better, so better do it next time, and I will have a little more time. I should be done about now. So you can, if you want to do something, you can remember what was the orthonormal matrix. And it has some special property. It has the special property that inversion of orthonormal matrix is just transposition. And I will, there is some subtlety which I'll explain on Wednesday, okay? Can I leave you with a slight overhang? Okay, any questions? Okay, thank you.